Let's talk about exponential growth and decay. Now, when we start talking about this subject, we really first want to understand what a differential equation is. And a differential equation is an equation involving derivatives. So when you see an equation and it's a differential equation involving derivatives, its solutions are actually functions. Okay. So usually we're used to a solution to an equation being a number, but this time the solution to our equation will actually be some function like y equal to f of x. So we're really going to focus our studies on this section to one very specific type of differential equation. And this is the differential equation that looks like this. So let me highlight this differential equation right here. Okay. And I want to unpack this differential equation with you. So let's look at the left-hand side of this equation first. If you look at the left-hand side of this differential equation, we can view this left-hand side dy dt. This is really the rate of change of some quantity y with respect to the time t. In other words, y is our independent variable and t is the dependent variable. Okay, so that's what the left-hand side represents. Let's look at the right-hand side now. On the right-hand side, you see k, which is a constant. So this k is a constant. And then we see y on the right-hand side again. So this y is the same as the y up there. Okay, so what is y? Y is really a function, and it represents the amount of something. And just to be explicitly clear, it still depends on t, right? So y is a function, it's the amount of something, and that amount changes depending on the time. So how do we put both sides of this equation together? So this particular differential equation says that the rate of change of y, which is the left-hand side over here, is proportional to how large x is. So when I see that dy dt is equal to some constant k times y, that means that the rate and the amount are just proportions of each other. This means the bigger y is, the bigger the rate of change. Right? So as y gets bigger, it grows faster. So this is what we call like a snowball effect. Right? You can imagine a snowball rolling down a hill, and at first it starts off kind of small, but then, the bigger the snowball gets, the faster it rolls down the hill, and it keeps getting bigger and bigger and bigger, exponentially large. So if we look more specifically at this, our differential equation again, what do we notice? We know, okay, the rate of change is proportional to the size of the function. And this constant k is what we call a constant of proportionality. So let's look and investigate what happens for different values of k. So when k is greater than 0, when that occurs, then we say that we have a law of natural growth. In other words, the derivative is going to be positive, which means it's growing. When k is less than 0, then we're going to have what we call a law of decay, the law of natural decay. And that means the amount is getting smaller and smaller. So growth, things are getting bigger. Decay means the amount is getting smaller. All right. So let's investigate what solutions to our differential equation might look like. Now, when we look at this differential equation, we see that the derivative is related to the original function. If I start off with my equation, y is equal to e to the t, well, this equation basically says that the derivative is equal to itself. So this is a solution. This is a solution if k was equal to 1. Well, what happens if k is not equal to 1? We know that we have the chain rule, right? So let's take a look at another possibility. If I put y is equal to e to the kt, and then I were to take the derivative of that guy, let me take the derivative of both sides. I get dy dt, differentiating the left, you get that. If you differentiate on the right, you're going to get the derivative of e is just itself. You keep the insides, you keep the kt like this, and then you multiply by the derivative of the inside. The derivative of kt is just k itself. So then if I write it like this, we can see, oh, that's basically saying dy dt is equal to k times y. This shows that y equal to e to the kt is a solution for really any k. So then the next question is this solution that we just found, is this the most general solution? And the answer to that question is no. There is an even more general solution that we can find to this equation. And the more general solution is a simple modification. We take that y equal to e to the kt, and then we can really multiply by any constant in front. So let's check to see that this guy is also a solution. So I'm going to differentiate both sides again. When I differentiate both sides, I'm going to get dy dt on the left-hand side. And on the right-hand side, I have to use the constant multiple rule. So the k stays there, the c stays there. And then I'm left with taking the derivative of e to the kt. Well, I already did that. That derivative of e to the kt, that was right here. That's k times e to the kt. So I can just write that down again. So then this gives me k times e to the kt like this. And if I just simply manipulate this a little bit, you can see that we get dy dt is equal to k times c e to the kt. But remember, this whole thing right here was originally our y. So, so really this becomes dy dt is equal to k times y. So what have we done? We've shown that we can find this, a function that looks like this is going to be a solution to our differential equation. Our more general differential equation, dy dt is equal to ky. So there's a theorem, which we're going to talk about now, that says, not only is this solution we just found a very general solution, but really it's the only solutions to this differential equation are that. So the only solutions to the differential equation dy dt equal to ky are y equal to c times e to the kt. All right. So we started off looking at a general differential equation, and basically we've solved it. We know what the solutions are. A lot of times you'll see people really write it as P of t equal to C e to the kt. Why do they call it P of t instead of just y? Well, y would be a generic name for a function, but when we write P of t, P generally you could think of that as population, and t you could think of as time. Remember, we have an independent variable of t, so when you write P of t, that indicates its dependence on time. Some of you might be wondering, is there something special about this letter C? And there is something special about that C. That C is frequently called the initial population. And we can see that that's going to be true because when you substitute in a 0 for t at time equal to 0, that's the beginning, right? This whole e to the kt part is going to become a 1. And then you're going to get that your initial population y is just going to be equal to that c. So that's why c is frequently called the initial population. So really the solutions to this differential equation are going to be a whole family of functions. And this whole family of functions may have different initial populations, but they're going to have this general shape. Okay, let's talk about relative growth rate. Relative growth rate is a constant k that measures the rate of change relative to the population size. So we can really find the relative growth rate by using some simple algebra. We know that our differential equation looks like dy dt is equal to k times y. Now what I could do is I could divide both sides by y. If I divide both sides by y, I get k is going to be equal to dy dt in the numerator, and in the denominator we got y. So I think we could see that this is the growth rate divided by the population size. So by looking at this, we can see that k is the growth rate relative to the population size. Okay. So this concludes the basics of exponential growth and decay. We'll look at some examples in class that will really make this a lot clearer. Take care, everyone.